Hi everyone, my name is F Ciappina and I'm a PhD student at UCL. My supervisor is Professor Faria. This is my companion video to my poster on photoelectron holography and beyond Born type methods. Bit of a mouthful, eh? Hope you enjoy. What is photoelectron holography? Well, it's used for ultra-fast imaging of matter. It allows retrieval of transition amplitudes and phase differences, so we can build more of a picture of the target. And it's high photoelectron current and high resolution, so it's an incredibly robust form of imaging. The advantage of using non-Born type models is that you have the ability to probe further. Interference patterns can be linked to specific orbits, there's phase differences, and it's more realistic. So the model I use is the Coulomb quantum orbit strong field approximation, which is an improvement on the SFA by adding the Coulomb potential into the continuum. So why do we use orbits? Orbits provide a physical representation of the recollision picture as seen by the three-step model. And the interference patterns that we plot show the interference structures between the orbits and the interaction that they have on one another. This also indicates types of scattering, and we're able to establish who does what and what role do each orbit and pairs, even triplets of orbits, play. So where do these orbits come from? Well, we don't just pull them out of thin air. They come from the mathematics behind the model. Formed from the S matrix theory and scattering amplitudes, we use path integral techniques combined with saddle point approximations. The saddle point equations derived from the action give us the four orbits that the electron may follow. This contains the quantum prefactor, so bound state information is included, an improved transition amplitude, and a stability factor. What type of scatterings occur? Well, in our model, we see that orbit 1 and 2 are direct, whereas 4 is rescattered, but 3 is some sort of hybrid between the two. So let's analyse what these types of scattering mean. In the SFA, we only have direct and rescattered. It's a very binary approach. And thanks to the Coulomb potential being added into the continuum in the CQSFA, we're able to see that it isn't so binary, and we have a third hybrid orbit. So, what is rescattered? What is direct? Direct is where you have the ion and the detector, and the electrons go straight to it. Whereas rescattered is you have the ion and the detector, but the electrons can leave, come back, and then go to the detector. Therefore, it's the longer path. So, what is our hybrid? In our group, we fondly call it the in-betweener, because if you look at the pontomotive energy cutoffs, direct is always at 2 UP, whereas rescattered is at 10 UP. Therefore, the in-betweener lies somewhere in between. This can be seen in my PMDs on my poster, that there is a spilling out of the direct cutoff. So, what has the CQSFA shown in this project? Well, we've shown that rescattering is not limited to the polarization axis, and this is due to the spilling from out of the 2 UP region more into the 10, but not actually at the 10 boundary. Also, the model produces quantum interference patterns and the ability to probe core dynamics and match them with specific orbits. And this is shown by the structures, and when we deconstruct the structures, wow, that is also a mouthful, we're able to see how the orbits interact with one another. We've also shown that direct / rescattering is not as binary as the SFA suggests. Orbit 3 is a hybrid, like we've shown in the spilling and the structures again. We're also able to observe the signal of perpendicular orientations to the state, to the field, without the use of perpendicular fields. So this is the real bonus of having a non-Born type model. And the inclusion of the Coulomb potential has strong influences in the field dynamics shown by the suppression in the momentum distributions. So my poster is on the conference Twitter page. You can also follow me on Twitter too if you have any questions or comments. So thank you so much for watching. Stay safe, be kind, and focus on the science.